Introduce the second of our Walter Reed Associated teams, WRVL.
Good afternoon, everyone. I first want to say thank you to our professors, to Walter Reed, to our sponsor, Dr. Gilman, and to the Johns Hopkins Veterans Health Institute. Before we get into the nitty-gritty detail, I want to first bring up our population that we're trying to help. Not every GI is a Joe. And what this is specifically referring to, which is it's a slogan coined in 2014, is the 2.3 million female veterans that are retired from combat. And out of these 2.3 million, there's 2,100 female veteran amputees. This is Army Sergeant Brenda Reed. She lost her foot and her ankle in combat. And she's been, well, I guess you can see her here holding what you call prosthetic, but she calls it her man's foot. She's had it shaved down, she paints it with red nail polish, all to make it more feminine. So, and here you can see she's saying, I want a foot that fits, a female foot, because men's feet and women's feet are drastically different things. So we first thought about going into some background about heels. And I know about the 12 women in here all know about heels, but on average they're 2 inches, 2.03 inches across the US. And a lot of these states are actually higher and closer to 3 inches. So this got us thinking, well, what kind of prosthetics can female veterans wear if they want to wear heels? So we started looking at some. Up here you can see the discrete one, which means that if you want to wear a 1.63 inch high heel, you can't wear it if there are only discrete locking positions at 1.5 inches or 1.75 inches. The rest of these are all, they're infinitely adjustable, meaning you can go to any position. However, all of these prosthetics can only go up to 2 inches, which is below the national average, 2.03. So it got us thinking, well, how do these work? So we acquired a couple of prosthetics, the discrete one and then these two right here. But after reverse engineering it, we were still a little bit confused about how women are able to walk in prosthetics in heels. So that brought us to how do people walk in general. Up here you can see at the very top that when you walk there's a rolling motion. And what is so natural to us is not natural to those with amputations. You have your dorsiflexion, which is up here, and your plantarflexion when you plant your foot on the ground. And that's something we do naturally. So this brings us again to the high heel issue. If it's already difficult to walk in a prosthetic limb without heels, then it must be even more difficult to walk with high heels. So here is an unacceptable prosthetic for 2-inch heels. This prosthetic does not adjust for different heel heights. But you can see here that it's slightly angled. So this will make it difficult for the female amputees to walk in. They'll hobble, they can lose their balance, and this could lead to more issues. Here's an acceptable one where you can see that this prosthetic adjusts for a 2-inch heel. Yet using that same adjustable prosthetic, it cannot adjust to a 3-inch heel. And again, you have that similar problem that is shown in the first figure. So that brings us to our project objectives that Joey is going to talk about.
All right. So here's just a basic overview of some of the things we were looking for in our prosthetic ankle. So we want it to be adjustable for heel heights 0 to 4 inches and infinitely adjustable so you can get those heel sizes that are in the 100th place with the inch height. So we want to have no tools to adjust them so they can adjust it whenever they put on their foot in the morning. They don't have to go get their special prosthetic key. An individual 125 to 250 pounds that supports a lot of the female population. Want it to weigh less than 3 pounds so they're not clunking around this huge iron boot when they go. And normal ambulation and natural gait so their walking stance looks natural when they wear it. Secondarily, we'd also like to use minimal to no electric power so they don't have to charge their foot every few weeks or however often that may be. And we want to achieve a 95% satisfaction rate from the survey of people who do end up using our prosthetic. So here's our proposed solution to prominence. It has 5 main components, as you can see here. So number 1 is this is the cosmesis shell. It gives the foot the overall aesthetic look, and it'll help with some of the toe dorsiflexion. And number 2 here is the foot plate. It's just carbon fiber. It gives it the rigidity. Number 3 is the ankle mechanism. It helps actually turn the ankle joint so they can adjust it to higher angles. We have a cam lever here to put the confining pressure on it. And the last one is the Avalon. We'll go into more detail in each of these a little later too. So here's a picture of the prominence in the flat heel condition and the raised heel. You can kind of notice right here the rubber will bend to get the toe flexion a little bit. So here's our prototype we created in the flat heel position, and then the next is the elevated heel position.
So next, we wanted to look at how the user will be using this foot. First, we picture the user as having worn flat shoes, having their foot in a flat, neutral position, similar to how we have the prosthetic set up on the table. The user then decides, hey, I want to wear my 3.5-inch heel for the night, I want to look good, I'm going to put this on. What they first do is they first insert the prosthetic in the flat position into the shoe. The flexibility of the material in the front part of the cosmesis is then going to allow the toes to conform to the shoebox as it slips into the foot. Next, they're then going to use the cam lever to reduce the compressive forces on the frictional disc mechanism that allows for the larger amounts of adjustment. They will then push the entire apparatus back, bringing it in line and lining it with the rest of the body, having to go through hips and shoulders to achieve proper gait. At such point, then using the cam lever system, they will then add compression back to the friction disc mechanism, locking that into position. As they then can stand up and test whether the system's in alignment. If it is, then they're all set to go. They should have good ambulation, natural gait, and good walking. If it's not, if they have it a bit out of alignment, then they can go back to step 4, unlock it, try to get the device back into position, and then relock it and continue and recycle that process however much they need to be able to find the natural position.
Alright, so I'm going to talk to you a bit about the foot plate. So there's a few things to note about this. First off, you might notice that this is a cylinder instead of a rectangular cross-section here at the end. This is very important because you imagine as the heel height is raised, if you had a rectangular end, it would be essentially a point contacting the ground, which would result in very high stress concentration, as well as the fact that it could damage the cosmesis. It's already been touched on that this cylinder here is where the toes would connect to the ball of your foot. It doesn't extend the full length of the foot. This is because this material is too rigid to be able to flex, to be able to fit into a high heel shoe. And this also allows cosmesis to give some degree of stability as well. You'll also notice that it mimics the arc of a natural foot, which allows some degree of flexibility and dynamic energy return. And then this curve at the end also mimics the natural foot and allows the cosmesis to be able to hook onto the foot and not slip off. So, of course, we wanted this to be light and strong, so we went with carbon fiber. In our most recent iteration, we machined a mold using a wire EDM from aluminum. We then took unidirectional carbon fiber, which means the fibers are all running in the same direction, coated them with resin, and oriented them lengthwise along the foot, clamped it with an immense amount of pressure, and then once it had cured, we just released it and polished it up a little bit, and then that's in its current state, as you can see on the table.
Next, I'm going to be talking about the disc mechanism that we use to adjust and lock the ankle. As you can see, the center of rotation for this mechanism sits a little bit below where the natural ankle's center of rotation would be. This is because of the complexity of the natural ankle, and in the process of simplifying it to make a prosthesis, it is common to actually have the center of rotation be a little bit lower. The exact location of the center of rotation is determined through gait analysis, which Luke is going to talk about in a little bit. Our prototype uses a collection of aluminum discs that, when compressed, create enough friction forces to lock up the ankle at whatever heel height you desire. Eventually, we're intending to transition to titanium, which will improve strength and be lightweight, which is very important for a prosthetic foot. Our current design uses a 2-inch diameter, disc, which simulates roughly the size of the natural ankle. This is very important that the ankle appear to be relatively close in the same size to the natural ankle so that it does not draw any attention to the user's prosthesis, which is very important for a majority of prosthesis users. Finally, I'm going to talk a bit about one of the calculations that we did. We analyzed our design in loading and in friction, which are our two most important factors when designing a prosthetic foot that uses friction to lock. Eventually, our equation for torque due to friction arrived at this equation in the top right, which basically just relates the torque due to the user's weight given their given the prosthetic foot as the moment arm, which is as soon as the user is lifting their heel, the entire foot makes up the moment arm. So using that scenario and the user's weight, we came up with this equation, which basically just states that the torque due to friction is a function of the number of discs, the coefficient of friction, the normal force, and the dimensions of the discs. This is pretty intuitive, but it allows us to model, the ideal geometry, material, and number of discs.
So for now, I'm going to talk about the final element of our design, the Avalon prosthetic. The Avalon prosthetic is a piece taken from the End-like Avalon unit that is sold as a separate foot. What this unit is a hydraulic that allows for flexibility of the foot, duplicating normal dorsal and plantar flexion with 6 degrees motion in both directions, allowing the foot to move during the normal gait cycle as it would naturally. This better replicates it because normally the foot rolls as it's coming down, and then the system can duplicate it such that you are able to better achieve a natural gait, and the Aptitude has a more standard gait to them, and you can't see that there's a difference, and it also saves energy as such. Going forward, we have, with our initial prototype, already been able to succeed on some of both our heel heights in the range we want, based on some calculations with the ankle circumference. It looks like we'll also be in the foot shell once we do a bit of trimming on the carbon fiber foot plate. Our adjustability is very good. We have a full infinite range. There's no tools needed to do it. It's just with the cam label. Next semester, we'll be testing it with lot of weight and also multiple cycles to be able to arrive and see its durability. The weight is also below the level that we want. And I'm shortly going to talk about the gait testing that's going to allow us to look at the natural undulation. We'll be holding a shoulder as well. And additionally, there's no batteries, no electrics on that, so no power usage. One of the other device we have on the table is our able-bodied prosthetic. What that allows us to do is allows us to wear the device. This then will allow us to simulate gait in the prosthetic. This is a common technique used by multiple companies in the industry to research and look at their designs. We currently have it attached with the oscillation foot that you can see on the table. This is going to be very critical as we use the gait analysis that you can see, picture two that I'll get into very briefly, to be able to analyze the gait on the new prominent foot. What we did this semester with the gait analysis is we ended up doing static position tracking so that we could determine the ankle location. You can see on the left side picture, Kate's wearing a number of Vicom dots with then a close-up on the right side. These dots allow the 26 cameras in the room to triangulate and locate those positions in space. That then allows us to set up this frame model to then track and see how she's standing, and future how she will walk in the space, allowing us to arrive at gait data. Using the data we have collected in the static frame, we, across multiple high heel shoes, which give us a range of heel to toe drops that we've normalized for the platform and for the foot position, we then can arrive and look at how the ankle is moving as we change the heel to toe drop in the shoe. This data will then we can then compare this data to how our new prosthetic performs to see whether it's duplicating the way that the human body would function. Additionally, we now going forward in terms of the resources that we have only spent approximately 1/6 of a budget. This puts us in a very good position for moving forward in the next semester, as we have a lot of resources that we can draw upon if necessary. We are already in a very good position with the prototype we have and feel confident that we can refine that to improve it. We are hoping to apply some of the titanium printing facilities at Walter Reed to be able to make it stronger, and also refine the design to make everything more compact, and with the development of the cognition, which was one of our main tasks for this upcoming semester, really pull everything together. Now I open the floor for questions.
Jay, please.
Just a quick question. It was a great presentation, great slide. You mentioned mentioned that hydraulic foot. What's the relationship there?
Okay, so
Yeah, that.
basically, so I'm going to try to demonstrate this. When people are walking naturally, your foot rotates in you. There's an angle I have going down here, and then as I move through gait, it changes.
No, what I meant was that device is apparently available.
Yes.
How does that compare to yours or
So
why? One mention.
because we want to get that sort of movement in the gait. And this is the hydraulic inside it is already very tiny and very difficult to manufacture. The company Endolite who makes it only mounts it to a flat foot. What we're doing is adapting it and using it on top of a large mechanism to be able to achieve the full spectrum of movement.
Okay, that answers.
Great off-the-shelf solution, yeah.
Thank you.
Good research. Dr. Morrow.
Yeah, so I remember back in September, that rhymes, that you guys visited me when you were starting this, and we're wondering about what different types of footwear you were even being asked to consider. And I'm glad that you kind of focused down onto high heels, but you were also talking about maybe boots. And I'm wondering, could your solution be adapted to different types of footwear besides high heels, and could it also have some use by the male soldiers?
So great question. So one of the great things about the solution that we have right now is since it can go foot flat, it should have no problem being able to be used in a boot as is once it's fitted with the cosmesis to be able to fit at that shoe size. That would then allow them, they might not need the same range of motion in terms of raising the heel, because I don't think most guys will be wearing 4-inch heels anytime soon.
Most boots are around 2
Yeah,
inches, so it's the equivalent of a low heel.
Thank you.
Adrian?
So you guys said that at the beginning that there are 2,000 some odd female amputee veterans. So I assume you want to sell this to more than 2,000 people. So would this be kind of like competitive in the marketplace for regular prosthetics that male amputees wear?
Okay. So when we talk outside of, so the military has some spectrum that goes to one side of the gender, and as the military integrates more, especially with recent things in the news, that's going to split across the board more evenly. Certainly across the entire space, it divides pretty evenly down gender lines as to who needs what feet. Certainly the space is pretty well active in products that go up to 2 inches, so our product in being able to go to that 4-inch range and really cover the entire spectrum of high heel shoes available on the market is a feature that no one else has. So that certainly would be something to look at, but that would also come as the position that Walter Reed fills is to help veterans. We're looking at it really from their perspective right now. If they'd be different, if they'd want to either work with a prosthetic manufacturer like ASA or Freedom Innovation, this could be developed into something that would then be an item in the market.
There is a large population of people who have diabetes and who have lost a limb due to that. So while we understand that there is that population, we want to really represent the female veterans who are, in a way, still underrepresented right now, and they have issues getting health care. So that's who we're primarily targeting to, but this will be applicable to a wider population.
I want to kind of change gears and talk about your analysis you used. Can we go and look at the slide of the vision tracking that you guys use?
Sure.
I wanted to understand, how did you get involved with a group that did this? I thought this was a really, I'm a big fan of new approaches to things.
Okay.
Analysis. Can you talk about this more?
So yeah, certainly. This is actually one of my favorite things. So this is actually, so Walter Reed has a very, very incredible facility for this. They use it a lot in looking at their patients and giving the prosthetists an ability to see really how they're moving with the gait to make fine adjustments to really enable the best patient satisfaction. This has actually been applied throughout the whole industry, both on the development side and then on the treatment side. So to give fair credit to the industry, they were using it, and we've adapted it slightly with some of the static data positioning we've done, because there's not been that much in terms of high heel trials or really anything there. And so this really allows us to locate stuff in space, and especially if we then move into next semester and we start really processing data related to full gait and motion.
Now, can I ask you, the data that you have on so this is great, the actual data that you got. In terms of analysis, this screenshot, that one there, are you able to actually pull information out of this analysis software? What software are you using currently for this?
So the entire system at Walter Reed, based on my understanding, this is all done in Viacom, which is a marker set we're using. There's another program that allows us to even extract more information by post-processing it and interpreting it, Gradle. But for at least that data we were processing now, the Viacom software was sufficient for us to be able to track and understand how, for our goals here, the 3D, I don't know the name, but it's not 3D mark, it's something similar to that, that you can additionally analyze the data more, and it's a bit of a cleaner interface, which we will probably be using as we move into the walking. Yes.
And based on your experience, do you think that this kind of analysis is possible for the general public to be able, not general public, but like the students to be able to use? Like, for instance, when I was going to school, we were just starting to use 3D printers, and now we got 3D printers in every single project. Is this sort of motion? A lot of the projects are like, we've been talking about how it fits together and how they can actually use it for ergonomics. Do you see this, you expose it now, do you think that you'd be more likely to use this in your field in the future?
This was a fantastic resource to be able to utilize. It, in that way, was really cutting edge. It's sort of, because when we first approached this, I actually first tried this using my camera phone and then a piece of plywood I put tape up on and then mark. However, so it was a much less quality system than the $20-some million setup they have down there.
Anyway, I want to talk about you more.
Yeah.
I'll talk about with you afterwards.
Yeah, no, so sorry. I do think it could play a large role, because there's a lot of things it can facilitate.
Yes.
One obvious question, have you tried, or a lady tried using this assistant?
Not quite yet.
No.
So you don't know whether it works?
Well, we can show you, we can demonstrate now, or if you will, that it does move and adjust. We did have, however, some manufacturing issues that have created eccentricities in some of the parts that we don't that wouldn't enable testing at this stage. We want to refine some of the manufacturing before we put it on anyone, especially because it would be a medical device. And before we ever put it on anyone, we use the able-bodied prosthetic to.
Yeah, currently there's aluminum here, so it would shear quite easily if we put body weight.
However, the amount we were looking to actually fill this range up more and potentially use titanium discs, which will be much stronger.
So you're talking about failure modes, and so are you going to do some stress analysis on
Yes. So next semester we are planning on doing a lot on both a straight physical loading test on it from this direction on body weight, and then also cyclic testing to be able to see how it's going to
Yeah,
proceed.
you had that in your plan, I just
Yep.
didn't see the actual, what kind of stress analysis you're going to do. No, it's in your plans.
Yeah, yeah.
Unfortunately, we really do have to leave it there. But remember,